Okay. So in discussion for the problem 1, we have S1 to Sn. They are from simple random sample. That means the sample without replacement. So if Si and Sj, they are not independent. Okay. And in the lecture, we know that there is an unbiased estimator for sigma square. Okay, this is the unbiased estimator. So that means the average of this will be sigma square. Okay. Here the S square is the sample variance. Okay. So we want to prove the following statements. The first one is S1 to Sn are either 1 or 0. Then this quantity is an unbiased estimator for sigma square. Okay. Okay, question 1. So we know that the unbiased estimator, the method for sigma square is S squared divided by n 1 minus small n big N. Yes, okay. So here what we have to do now is we have to write the S squared to see what happens if the S1 to Sn are 0 or 1. So the S squared is equal to this summation Si minus S bar is power 2 alpha 1 to n. Okay. And this is also equal to summation alpha 1 to n Si squared minus 2 Si S bar plus S bar squared. Okay. And this can be like this. Si squared plus 2 summation Si S bar plus n S bar squared. Okay. And we know that the sum of Si is equal to n times S bar. So in here, we can get the negative n S bar. Okay. So now what we have is like this. Si squared minus n S bar. Okay. And next step, we want to change Si. Okay. When Si is either 1 or 0, Si squared is equal to Si. So now we can have, so here is because Si 0 or 1. So now we have the, okay, multiply n here. So we will find that's n. Then we can get the S bar minus S bar squared. Okay. So what we get is this. S bar 1 minus S bar. Okay. So S squared is equal to this when Si is 0 or 1. So we plug in this into here to get the aspirant estimator for sigma squared. So okay, define the estimate that this is equal to S bar 1 minus S bar divided by n minus 1. Yes, 1 minus n divided by big N. Okay. And in question 2, we want to find the suprema of the estimator, this one. Okay. So we want to find the suprema of P, sigma h squared P. This is equal to suprema of P p 1 minus p, and multiply the constant is this. Okay, so this part is p 1 minus p, and here is the constant. So here this is constant, so it doesn't influence the optimization. So we only have to calculate this one. Okay, so we can define fp equal to p 1 minus p, and we find the first derivative of this is equal to 1 minus p, and we solve this equal to 0. We can get p equal to 1 over 2. Okay, so when p equals 1, 2, this is a local maxima or minima. And now we have to find the second derivative, which is -2. So that implies the f is concave. This is negative, so that implies f is concave. So that implies p equal to 1 over 2 is maximum. Okay, so fp is equal to, I say this is p star. P star equal to 1 over 4. So if we plug in this one to here, we can get a suprema. So the suprema of this is equal to 1 over 4, and the constant is 1, and 1 minus n, big N. Okay. Okay. And the next question is, we want to apply the central limit theory to check this commutative is 1 minus alpha commutative for all view. Okay. So I want to check. So this is sufficient to show that the probability of mu belong to the commutative is bound minus z to alpha. Okay. Sorry, these two. Okay. So now I define this one is equal to sigma star hat p star hat 2. Okay. So now we can use this notation. So this is, and the upper bound of the interval is this. Okay. Yeah. And this probability is greater and equal to 1 minus alpha. Okay, so this is question mark. So now we calculate this probability. Okay. So this probability is equal to mu smaller than greater than s bar greater than left tail, smaller than right hand side. Okay, and we do some rearrangement. You can find, you can look at this. Okay, no. Okay, and now let's say we want to apply the central limit theory. So we have to divide it by its variance. Divided by sigma hat s bar. Is s bar. Okay. Then we apply the central limit theory. We know that this quantity is approximated by z. So this is would be, the probability can be like this. Okay. Here's x bar, and smaller than z. Okay. So then we can see this quantity and this quantity should be greater than or equal to 1. That is because this quantity is equal to P-man of this. Okay. So this always greater than 1. So then this also greater than 1. So that means this probability is greater than smaller than greater than or equal to this. Okay. So if we choose the smaller constant, so the probability may be smaller, and we know this is equal to 1 minus alpha. Okay. So next question 3. And then the property, we want to find the unbiased estimate for mu square under simple random sampling. Okay. Okay. Here I want to find the average of this S bar square. This is equal to variance of x bar plus mu square. So if we can estimate variance of S bar, then we will be able to estimate mu square. Okay. Okay, so for the lecture, we know that the unbiased estimate for variance of S bar is like this, sigma square. No, sorry. We know that under simple random sample, variance of S bar is equal to sigma square divided by n, and big N minus small n, big N minus 1. Okay. And we also know that the S square divided by n minus 1, 1 minus, no, yes, let me check. Yes, it's the same. Okay. This one is an unbiased estimate for sigma square. So if we plug into S sigma square, then we can get unbiased estimate for variance of S bar. So S square n 1 over n 1 over small n is an unbiased estimate for various S bar. Okay. Then what we have done is s bar square minus this quantity. Let's copy it and paste in here. Is an unbiased estimator for u square. Okay, that's all.